Now we understand that alkyl halides undergo two types of reactions, substitution and elimination. And within substitution, there are two mechanism types, SN2 and SN1. In SN2 reaction mechanism type, the two events, the nucleophilic attack and the departure of the leaving group, take place at the same time. The SN2 mechanism, therefore, is a one-step reaction, if you like, or a one-step mechanism. On the other hand, in the SN1 mechanism, the nucleophilic attack event and the departure of the leaving group do not take place at the same time. They are in separate steps, and that's why an SN1 mechanism type consists of two steps. It's a two-step mechanism, the SN1 mechanism type. Now, in the substitution reaction, of course, a nucleophile is going to attack a substrate and a leaving group is going to leave. Whether the mechanism is SN2 or SN1, a group will leave, a nucleophile will attack an electrophilic carbon, and of course the reaction is in a solvent, and therefore the reacting parameters in substitution reactions are the nucleophile, that's the first parameter, if you like. The nucleophile is going to attack, so it is very important parameter in the substitution reaction. The substrate, how big it is, how small it is also very important in the reaction. The group that's going to leave, or the group with the ability to leave, or the leaving group is also important. The reaction is carried out in a solvent, so the solvent has also an important role in the reaction, or in the determination whether the reaction is SN2 or SN1. So there are four variables here, there are four parameters in the substitution reaction. Let's now talk about each of them separately, and we compare the role or the importance or the characteristics, if you like, of the nucleophile in the SN2 mechanism and also in the SN1 mechanism. Now, in the SN2 mechanism, the nucleophile is going to attack this carbon with simultaneous departure of the leaving group. So the nucleophilic attack and the departure of the leaving group take place at the same time. The nucleophilic attack and the departure of the leaving group take place at the same time in the SN2 mechanism reaction. Now, for the nucleophile to go and attack, it must be strong. It has to be strong, yeah? If it is weak, it will be sluggish to attack. It will not attack easily if it is not strong. So therefore, a very important feature of the nucleophile is that the nucleophile has to be strong. When we say strong nucleophile, then probably we mean negatively charged. So the nucleophile should be negatively charged if the mechanism is SN2. The nucleophile should be strong, and also it should be small. It is supposed to do a quick attack. It is supposed to go and quickly attack this carbon, and then L goes or L leaves. So if it is weak, it will be sluggish to attack. If it is bulky, it will also be sluggish to attack. Yeah, the attack will not be fast and smooth. Yeah, so the nucleophile should be small and charged, or small and strong, rather than weak and big, and that will hinder the SN2 reaction or the SN2 mechanism, and therefore it will not be SN2. So this is very important. The nucleophile should be strong and small. Examples of strong and small nucleophiles are the following. We have already taken hydrosulfide ion. This is a hydrosulfide ion. This is an example of an excellent nucleophile, hydrosulfide ion. The cyanide ion, Cn-, This is also an example of a nucleophile, an excellent nucleophile for SN2 mechanisms. Cl minus, N3 minus, the azide ion is also a powerful nucleophile in this mechanism. Thiolates, alkyl thiolates coming from thiols. Okay, these are the conjugate bases of thiols. Thiolates are also important nucleophiles as powerful nucleophiles or excellent nucleophiles in SN2 mechanism. So these are examples of nucleophiles that are suitable in SN2 reactions. A very important piece of information here also is that if we go down a group in the periodic table, the nucleophilicity enhances. If we go down a group in the periodic table, the nucleophilicity is enhanced or nucleophilicity is increased. So that's why CH minus, for example, methyl thiolate, is a better nucleophile than methoxide. So if we go down a group here, if we go down a group like that in the periodic table, then the nucleophilicity increases. If we go down a group in the periodic table, nucleophilicity increases. So that's why CH3 methyl thiolate, CH3 minus, is a better nucleophile than the methoxide ion. This is the structure of the methoxide ion. And similarly, the iodide ion at the bottom, or iodine at the bottom of the halogens group, the iodide ion is a better nucleophile than the bromide ion, which is a better nucleophile than the chloride ion, which is a better nucleophile than the fluoride ion. We don't put Cl minus or F minus here because they are not really very good nucleophiles in SN2. They are fair nucleophiles. The iodide ion is considered excellent. The bromide ion is considered good. So these are the ones underlined by red, by the way. These are all excellent nucleophiles in SN2 reactions. The methoxide ion is not as good, and the bromide ion also is not as good. So to conclude, the features or the characteristics of the nucleophile that should contribute or take part in the SN2 mechanism is that the nucleophile should be small and strong. In the SN1 mechanism, the two events, the nucleophilic attack and the departure of the leaving group, do not take place at the same time. The leaving group leaves first, or the departure of the leaving group takes place first, followed by the nucleophilic attack. In the second step, a carbocation intermediate is formed. So this is the carbocation intermediate that we discussed a while ago. The bottom line here is that the two steps do not take place at the same time. This is a two-step mechanism type. The SN1 mechanism is a two-step reaction or two-step mechanism type. Now, if we want to examine the importance of the nucleophile here, the nucleophile does not take role here in the first step, because the first step is departure of the leaving group. The nucleophile comes and attacks in the second step. So this is the second step where the nucleophile, so we can describe this as step 2, and this is step 1. So step 1 involves the departure of the leaving group. Step 2, nucleophilic attack. So the importance of the nucleophile lies here, actually, in step 2. So the nucleophile, should it be strong? Well, for us to answer that question, we need to look at the electrophile. Well, the electrophile here is a carbocation intermediate, and the carbocation intermediate has already a positive charge, an isolated positive charge. So the nucleophile doesn't have to be strong. The nucleophile does not have to be strong because this electrophile is already a highly electrophilic intermediate. This is already a highly electrophilic intermediate, so therefore the nucleophile does not have to be charged, it doesn't have to be negatively charged, and also the size is not really a big issue here. So therefore, the nucleophile here it doesn't have to be small or strong. In other words, a neutral nucleophile will do the job. A neutral nucleophile can participate in an SN1 mechanism type. Of course, the neutral nucleophile, whatever the nucleophile is, by the way, it must have always and again and always, it must have a lone pair. So the nucleophile here in the SN1 mechanism should be neutral. So a neutral nucleophile is enough to participate in the SN1 mechanism. An example or examples of neutral nucleophiles are water. So water is a neutral nucleophile, it's not negatively charged, so water is an example. Another example is amines, amines in general, amines with nitrogen that has a lone pair. So these are neutral nucleophiles which can participate in the SN1 mechanism. Unlike the SN2 again, because in the SN2, the nucleophile is going to attack quickly with simultaneous departure of the leaving group. So the nucleophile should be small and strong. Unlike here, the departure of the leaving group takes place, the electrophilic carbocation intermediate is formed, and then the nucleophile comes. So the nucleophile now will react with a highly electrophilic intermediate, and that's why the nucleophile does not have to be strong. A neutral nucleophile will do the job in the SN1 mechanism. The substrate in the SN2 mechanism should be a molecule that should facilitate the nucleophilic attack. Remember, the nucleophile should attack the electrophilic carbon with simultaneous departure of the leaving group. We already discussed the nucleophile, that it should be small and strong. What about the substrate? Well, the substrate should encourage the small nucleophile to come and attack it. The substrate should encourage the nucleophilic attack, which means the substrate should not be sterically bulky. It should not be big, it should not be crowded, and especially around the electrophilic carbon. Especially around the electrophilic carbon or the electrophilic site. The electrophilic site should not be crowded or sterically hindered. So therefore, the substrate should be sterically unhindered. This is a very important requirement, sterically not hindered. Sterically not hindered or sterically accessible. Okay, the substrate should facilitate the nucleophilic attack. Again, for it to facilitate the nucleophilic attack, it should be sterically unhindered or sterically not bulky or accessible. So therefore, the best substrate would be the substrate with the least steric hindrance around the electrophilic carbon. Remember, the environment or the crowdedness, if you like, the steric bulk around the electrophilic carbon is really the main thing here. So methyl substrate is the best substrate because this carbon is not substituted at all. Nucleophiles can come and attack this carbon easily. So methyl substrates are the best. They are greater in reactivity. So this is a reactivity scale, yeah? This is a reactivity scale in SN2. This is a reactivity scale in SN2 mechanism type. Methyl substrates are the best, followed by primary substrates. Primary substrates, basically carbon that's bound to the leaving group now has one R. Here it has none. Now it has one R. So this is methyl. Methyl is the best, followed by primary, followed by, of course, primary will be, and this of course will be much greater in reactivity than the secondary. So the secondary now will have two groups around the carbon or on the carbon that's bonded to L. So secondary substrates are also reactive, and they are much higher reactivity than the tertiary substrates. Tertiary substrates are virtually ineffective. The tertiary substrates are virtually ineffective as substrates in SN2 mechanism. So the most reactive substrate is the methyl. So these are the most reactive. Okay, this is the reactivity scale. Remember, the methyl substrates are the best, followed by primary substrates. So methyl and primary are the best. Secondary substrates can, by the way, they can take part in the SN2 reaction, depending also on other conditions, such as the nucleophile and the solvent, yeah? Okay? And actually, secondary substrates, they can do both, by the way. So we'll talk about that later on. So depending again on the nucleophile and the solvent, tertiary substrates are virtually ineffective, or they do not take part in the SN2 mechanism type. The substrate in the SN1 mechanism should be a molecule that can produce a stable carbocation. A molecule that can form or produce a stable carbocation. Why is this so? Because the carbocation intermediates are intermediates in the SN1 mechanism type. Remember, this is a two-step reaction or two-step mechanism where the leaving group departs first to form a carbocation, and then a nucleophile attacks the electrophilic carbocation intermediate. So the carbocation should be stable enough for the reaction to be of SN1 mechanism type. So therefore, the substrate should form a stable carbocation. So a stable carbocation is needed here in this SN1 case, and we learned before that more substituted carbocations are more stable than less substituted carbocations, and that's because of hyperconjugation or inductive effect. So therefore, it's not really surprising to see that tertiary carbocations are the most stable, and therefore tertiary substrates are the best now. So this is opposite to the trend observed in SN2 mechanism type. Tertiary substrates then were the least reactive or virtually ineffective. Here they would be the most reactive because they would be able to make a very stable carbocation as the SN1 dictates. So tertiary substrates therefore are the most reactive. Tertiary substrates are the most reactive in this case because they will produce a very stable carbocation, a tertiary carbocation. So this would then be more reactive than a secondary substrate that can lead to also to a secondary carbocation, which is also still stable. So a secondary substrate, we can write the corresponding carbocation actually, okay, below. So let's do that at the same time. So like that. So this is the tertiary carbocation that will be produced, and of course this would be more stable than the secondary carbocation. So tertiary substrate is the most reactive, followed by the secondary substrate, and this would be much higher reactivity than the primary substrate, because primary carbocations are not very stable, or if you like, not as stable as secondary carbocations or tertiary carbocations. And of course, the methyl cations will be the least reactive. So virtually, these are virtually ineffective really in SN2 type, in SN1 type mechanism. Yeah, that's because of the stability of the corresponding carbocations. So here then, the most reactive substrates in the SN1 mechanism are tertiary substrates, followed by secondary ones. We can also combine, by the way, in this reactivity scale, we can combine with a benzylic carbocation or a benzylic substrate and also an allylic substrate, because they will produce stable carbocations, similar, not identical, but similar in stability to the corresponding to secondary carbocations. So to this we can add, we can say similar to benzylic substrates or something like that can be added then. Yeah, this is a benzylic substrate. This will give, of course, the corresponding benzylic carbocation, which is this one here. And also, this will be, although it's a little bit more reactive, but similar in a way to the allylic substrate. So this is an allylic substrate, and this allylic substrate will lead to the allylic cation. So this is the allylic cation. We should label them. This is the allylic cation, and this is the benzylic cation, and the corresponding substrates are reactive. They are similar. We can put them here with the secondary. So all of these, the secondary substrate, the benzylic substrate, and the allylic substrate. So this is the allylic substrate. This is the benzylic substrate. These are also reactive. Their reactivity is comparable to that of secondary substrates. These three, secondary, benzylic, and allylic, they can be put together on the scale, and they will be of much higher reactivity in the SN1 mechanism, higher than the primary substrates, and even of course, much higher than the methyl substrate. So therefore, the most reactive substrates in the SN1 mechanism are the tertiary ones, followed by the secondary, benzylic and allylic together, and then primary. Primary and methyl are virtually ineffective in the SN1 mechanism. And the reason behind this is the stability of the corresponding carbocations. Tertiary substrates can form a tertiary carbocation. A secondary substrate can form a secondary carbocation. Benzylic substrate can form a benzylic carbocation. Allylic substrate can form an allylic carbocation. And although not mentioned, but you can predict that these carbocations are stable, and they are stable because of resonance. They are resonance stabilized, in addition to the inductive effect observed in the tertiary carbocation case and the secondary carbocation case. So if you wonder why these substrates are reactive, that's because of the stability of the corresponding carbocations, and these corresponding carbocations are stabilized by resonance. So this is the reactivity scale in substitution reactions. In SN1, tertiary substrates are the most reactive, primary substrates are the least reactive. In SN2 reactions or SN2 mechanisms, on the other hand, the most reactive substrates are the primary ones or the methyl ones, and the tertiary substrates are considered the least reactive.